hear me? So, is it time to start? Yeah. Okay. So the first few minutes I'll devote to what we were doing last time because I did not have time to complete it. So, so this is continuation of lecture 4. How to find one parameter subgroups. Of classical and of course by classical groups I just mean the SLN or the orthogonal groups. Okay, so what did we find out last time? One parameter groups of GL and RR of the form T goes to exponential of T times A, where A is some matrix, right? So, so one for SLNR. So what is SLNR? They are all n by n matrices with whose determinant is 1, and this is sitting inside GLNR, right? So every one parameter subgroup must be of the form e to the power of Ta, and whose determinant is 1. Okay, so every one parameter subgroup is of the form phi t is equal to e to the power of Ta, where t, and we must have now we must have determinant of now there is an identity in linear algebra. The determinant of e to the power of Ta is e to the power of 3 times trace of A. So so now determinant of e to the power of Ta is equal to e to the power of t trace of A. And what is trace? Sum of the diagonal elements. Okay, so for this to be a subgroup, one parameter subgroup, we must have e to the power of differentiate this now. What do you get? Trace of A times e to the power of Ta. So trace of A times e to the power of t trace of A is equal to 0. Okay, and since this is never 0, you get trace of A is equal to 0. So trace of A is equal to 0. Okay, so in particular one parameter subgroups of SL2R are A, B, C, D such that A plus D is equal to, okay. So this means this is of the type A, B, C minus A, right? And so this I can write A times 1 minus 1 0 0 plus B times 0 1 0 0 plus C C times 0, 0, 1, 0. So this will always form a vector space, right? So what is the basis of this vector space? 1, 0, 0, minus 1, 0, 1, 0, 0 and 0, 0, 1, 0. And you can compute so these are the fundamental generators. And what is the exponential of this would be e to the t, e to the minus t. And for this one I think it was 1, 1 and t 0. And this one will be 0, 1, 1 and 0 t. Okay. So these will be the basic one parameter subgroups, and there is a theorem that every element can be written as a not linear combination. These generate, because when you are in a group you don't talk about linear combination, just talk about products of elements where each of these is power of one of these basic one parameter subgroups. Okay. So now let's go to the orthogonal group. So what were those? These are all matrices such that A times A transpose is equal to identity. So O and R is, this is all n by n matrices such that A times, and A I have used for something else, such that M times M transpose, all matrices M, such that M times M transpose is equal to identity, right? So let's take, so take a one parameter subgroup. Because this sits inside GL and R, it has to be of the form e to the power of TA, right? So take a one parameter subgroup, phi t, what did I use for? Phi t is equal to e to the power of TA. Okay. So what is the condition? E to the power of TA times e to the power of TA transpose. So e to the power of TA, e to the power of T A transpose is the identity matrix, equal to 1, 1, 1 and 0 everywhere else. So okay, and then when you look at the power series for e to the TA, you can bring this inside. So this is e to the TA, e to the TA transpose is equal to the identity matrix, identity. Okay, ID because I am going to use for something else. Okay, now differentiate this using the product rule, but keep in mind that you have to that these matrices do not commute. Okay, so differentiate it. What is the derivative of this? Would be A times e to the TA times e to the power of T A transpose plus e to the TA times, differentiate this, A transpose e to the TA, and on the right hand side was constant, so we will get the zero matrix. So zero matrix. Okay. Now put T equal to 0, what do you get? What is e to the power of 0? 1, right? Identity. So A plus A transpose is 0. So A is equal to minus A transpose. Okay. And such matrices are called skew symmetry. And for you in physics, let's look at what happens for SO3. And these will automatically will have determinant equal to 1. So these are actually, so all one parameter subgroups from what I said before, because these will have, if it's a skew symmetric matrix, what is its trace? On the diagonal you have zeros, right? So the determinant has to be then 1, right? So all these are elements of SON. Okay. So let's do a specific example. Let 1 PSGs for SO3R. So this is A, let's give this some name, alpha, beta, gamma, delta. And what is A transpose?
Shouldn't be a 3 by 3 matrix because you.
Oh yeah. S3, yeah, you are, sorry, my mistake. So, okay, then, no, then we have to be a little bit more sophisticated. A11, A12, A13, A21, A22, A23, A31, A33. And what is transpose? You just rows become column. So A transpose this is A11, A21, A22, A23, A31, A32, A33. Okay. Okay. So A plus A transpose is 0. So A is equal to minus A transpose. So A11, A12, A13, A21, A22, A23, A31 is equal to minus A11, A12, A13, A21, A22, A23, A31, A32 and A33. So if you compute it out, so therefore, so A will have 0, 0, 0 on the diagonal. A12, A13 minus, or here will be A23, and this will be minus A12. This is minus A13, and this is minus A23. Okay. So what will be a basis will be, how many parameters do you have?
3.
You have 3, right? So this will be a 3-dimensional, actually 3-dimensional subspace of matrices. So basis is let's call it I, is 0, 1, minus 1, 0, and the rest is all zeros. And J is this 0, 0, 0, then 0, 0, 0, 1, 0, minus 1, 0, and K is 0, 0, 1, 0, 0, 0, minus 1, 0 and 0. Okay, and you can, okay, so you can verify that maybe I made a mistake, but you can verify that. So check if I bracket j is equal to k, j bracket k is equal to I, and k bracket I okay, the same thing which you get for the cross product of I, j and k. So okay, so as vector fields, what is Vi, the vector field corresponding to I? So first of all, as a transformation, we always look at it as a transformation. Okay, so the function defined by the linear transformation actually on R3 defined by I is xyz goes to 0, 1, minus 1, 0, 0, 0, 0, 0, 0, xyz. So to multiply this out, what do you get? Come on guys, what do you get? The y and then and 0. And what will be the corresponding? I told you, to every function there corresponds for every vector. So we think of it as a vector valued function. It assigns to the point x, y, z the functions whose first component is y and second component is minus x, third component is 0. So what will be my vector field? X, y times partial y partial x plus x times, no, minus x times partial y, and so thus Vi is y times partial by partial x minus x times partial by partial y. Okay, and similarly the vector field corresponding to j, what was j, would be, so if you would be
0z minus y.
0 z minus y. Yeah, so 0 z partial by partial y minus y partial by partial z, and for the kth, okay. So similarly, do it for, so do v the vector field corresponding to k as a homework. Okay, it's trivial. Okay, so that's all I wanted to say about these, how to. Okay, and now I come to the actual content of this next lecture. So can I erase this now? By the way, I've sent you, did everybody get the lecture in his,
Yes.
huh?
So in the language of physics, these are the generators of rotations around the x, y, and z.
That's right. These are the generators of the rotations around the x, y, z. Because when you compute the exponentials, you will get exactly the rotations around the x-axis, and you would have three parameters. Let's say theta 1, theta 2, and theta 3. and every rotation then can be written as a product of these, but in they don't commute necessarily, of course, right?
And yesterday they saw an example of killing vectors
जी जी जी
which preserve the
metric,
metric,
yeah,
which also has symmetries
which also has symmetries,
on a
बिल्कुल
sphere which are like this.
जी.
On a sphere they are these.
Okay. So what sphere did you take the SU?
Yes. Yes.
On S2. Okay. By the way, before I go, unitary group plays a big role in physics.
Yes.
So what will be the one parameter groups of G, L, and C? It should be e to the power of TA or e to the power of ZA, where Z is a complex variable. Because by definition a one parameter subgroup is a function from the reals to matrices, it has to be the e to the power of TA, where now A is a complex matrix, but T is the real.
Yes.
Okay, and you use the same. The definition for the unitary group is A times A bar transpose is equal to identity. If you plug in, then you will get the one parameter subgroups of SUN. Okay. जी
इस मेथड से हम ऑयलर एंगल्स फाइंड कर सकते हैं
किससे?
इस मेथड्स के थ्रू हम ऑयलर एंगल्स फाइंड कर सकते हैं
No. You for Euler angles you have to note that every rotation has an axis. Then you have to find the matrices, the linear transformations, which send one vector to this axis. And once you have this, then you know that every rotation around that axis can be written in explicit form. If you are interested, I can send you by email how to get it. I did it maybe 40 years ago, but I may still have my notes. Okay. परवेज इसकी फिजिक्स में तो बहुत इम्पोर्टेंस है ना इन चीज़ों की.
Euler angles?
नहीं ये all these things, how Lie algebras and
क्लासिकल में भी है क्वांटम कम्स लेटर
जी क्लासिकल में भी बिल्कुल होगी बिल्कुल. Because I don't think so you can understand quantum mechanics unless you understand Hamiltonian mechanics, right? There's some procedure called quantization. Okay. So this is very much close related to what you are doing in the other course. So this is lecture 5. How much time is left? 1 hour. Okay. Anyway, this is so important that even if we don't finish it, we will continue next time. Okay. So this is curvilinear coordinates. And canonical coordinates. Okay. And canonical coordinates for vector fields. Okay. So in the notes I took 2, but let's do general because I think now you can handle all these generalities. So we will work on open sets of Rn. Okay. So on open sets, let's give it a name U of Rn. Okay. Functions. So if f1 up to fn are functions on U. So they are functions of how many variables? N variables, x1 up to xn are functions on U. The Jacobian of f1 fn is by definition is the matrix let's call it J is the matrix J of f1 up to fn. So in the first row you will have partial derivatives of the first partial f1 by partial xn, and the last would be partial fn by partial x1 and partial fn by partial xn. Okay, so J f1 fn is the matrix whose ijth entry Aij is partial fi by partial xj, right? Ij running from 1 up to n. Okay. Now suppose that determinant of J, so let's give it a shorthand. So let J be the Jacobian. Okay. Assume P is in U and the determinant of the Jacobian, it's a function Jacobian at a point P is not 0. Okay. Then in a neighborhood of P, the function x1 xn, let's give it a name Q. The function x1 xn goes to f1 x1 xn and so on. Fn x1 xn is a one-to-one. One-to-one function means if 2 points have the same value, then they must be equal. Is a one-to-one function on a neighborhood of P, and it maps a neighborhood of P to a neighborhood of, let's give this some name. Let's give this capital F, neighborhood of FP. So maps it to an open neighborhood. Okay. So because it is one-to-one and onto, we call these functions curvilinear coordinates or generalized coordinates in your open set U. Okay. So for this reason, we call these. So we call we call these the functions f1 up to fn, curvilinear coordinates or local coordinates for defined in a neighborhood of P. Okay. So what example do you know already from Parvez's course? Polar coordinates, and you have the spherical coordinates. Okay. So they can be any functions whose Jacobian is not 0 somewhere, and in that neighborhood they can be used as S coordinates. Okay. So, so examples, polar coordinates and spherical coordinates. Otherwise, you have done this, right? Spherical, so I don't have to repeat, right? Okay. So just to so what is x in these in polar coordinates? R theta. What is x? In terms of r theta, huh? X is equal to r cos theta and y is equal to? Yeah. And what about in polar coordinates, rho, theta and phi? Okay. There's some formula.
But maybe you want to tell them about the Jacobian as a volume transformation element.
No, because I have not told them what a volume is, right? It would be an n form, and yeah, and then you can integrate against those n forms and.
Do it in coordinate language also. But let it.
Ji. When you change variables, I think that's what he's saying. When you change variables in, so you have a volume integral. Let's say you have a double integral, fxy dx dy. Okay. When you take new variables, then it would be not some f tilde uv du dv. It will be multiplied by the Jacobian. Okay. So anyway, so okay.
It's actually the determinant of the
Jacobian of the, sorry, determinant of Jacobian. Okay, okay. So now, so now, from now on, I just to save time, I will work only with n is equal to 2. I will work with n is equal to 2, because if you understand this, you can do it yourself in general. Okay. So let U be an open set in, because I'm going to use U. Let O be an open set in R2. Okay, and let UV be functions whose with Jacobian of UV not identically equal to 0. Okay. So I restrict my attention to the, I shrink this open set so that the Jacobian is never 0. Okay. So by shrinking O, we can assume that that the determinant of the Jacobian, that determinant of Jacobian of uv is never 0, is never 0. Okay. So now what is the chain rule? This is the key actually. So if f is a function of u and v, this is what you did in BSc, and I will give you a more sophisticated version later. So what is partial f by partial x? You have to look at all chains which end in x, right? So what is partial f by partial x? G. So partial f by partial x is partial f by partial u by partial x plus partial f by partial v by and partial f by partial y is partial f by partial u by partial y plus partial f by partial v by partial y. Okay. If we write this in matrix, what do we get? Partial f by partial x, partial f by partial y is equal to partial f by partial u by partial x and partial u, it will be a transpose of the Jacobian actually, partial u by partial y, partial v by partial x, partial v by partial y times partial f by partial u, partial f by partial. Yeah, I thought that maybe I made some stupid mistake. Okay, so what is this matrix? This is J transpose, right? So this is J transpose so partial f by partial x, partial f by partial y is the Jacobian transpose of partial f by partial u, partial f by partial v. Okay. So we can say that partial by partial x, partial by partial y is the transpose of the Jacobian, and this will be very useful when we solve PDEs. So partial by partial u and partial by partial. Okay. Hence, now so what is our main interest in this course are vector fields and their one parameter subgroups. So hence any vector field on O, hence as any vector field is of the form capital X is AXY partial by partial X plus BXY partial by partial Y. I've just shown you that this can be written as a function as a combination of partial u and partial v, and x y can be written also as functions of u and v, because the transformation to curvilinear coordinates is 1 to 1 and onto, right. So, so x can also be written as x is equal to, and this is the great freedom you get. X is equal to some function, let's call it a tilde u v partial by partial u plus b tilde u v partial by partial. Okay. So I have great freedom to choose coordinates and simplify my vector field as much as I like. Okay. So yeah. So this was just for illustration. In general, if I have a vector field in n variables and I have curvilinear coordinates, I can write the vector field in terms of those others, but using the transformation law which I just told you. Right? Okay. So canonical coordinates. So fantastic result. Okay. If x is any vector field, and now I can go to general. X is any vector field on Rn, defined on an open set O of Rn, and P is a point in U in O with xp not equal to 0. Then there are generalized coordinates or local coordinates defined near P. Then there are so I'll give it in two parts. One, then there are coordinates local coordinates, means generalized, they are not defined everywhere but near that point P. The local coordinates x1 up to xn defined near P with x something very simple, partial by partial x1. Okay. And this is not only a theoretical result, I will tell you how to find them. Okay. So, and the second part is if x1 up to xk are vector fields defined on an open set O of Rn, and and P is a point in O with x1p, xkp, not 0 but linearly independent, with x1p linearly independent. And I told you how to compute xi bracket xj is equal to 0. We know that xi bracket xi is 0 in any case, but if xi bracket xj is 0 for all ij, then you can introduce, then introduce coordinates x1 up to xn defined near P with x1 is equal to partial by partial x1 and so on, xk is equal to partial by partial xk. Okay. So in literature, I'll send to you today where you, if you're interested, where you can read the proofs of these results. Okay. But I'll give you some idea why this is true. So for proofs,
But Hassan, isn't this intuitively obvious?
not to me.
You have an n-dimensional space. You can construct orthogonal coordinates. D by dx.
There is no
takes you
geometry.
there.
There is no geometry.
If it's Rn,
No, but okay. So I mean, even in 1D, how will we do it? I give you a vector field x square partial by partial x. How will you straighten it out?
well, partial by partial x takes you in the direction of
No.
implicit x.
This vector field can be written as partial by partial x.
D by partial x can be treated as a
No. I have a vector. I have a specific vector field, v equal to x square partial by partial x, or d by dx. How will I write it as d by d x tilde? I have to solve something equation. So to find canonical coordinates, I have to write v as d by dx tilde, I have to find a function so that v of, because d by dx tilde is 1, right? D of something divided by is 1. So we have to solve x square So what is x tilde from here? Come on, Dr. Bakas has been teaching you. Dx tilde by dx is equal to 1 over x square. What is integral of 1 over x square? Minus 1 over x. Okay? So you have to do something. Similarly, if I give you y partial by partial x minus x partial by partial y, this is a vector field. How can I write it? You have to do something, okay? And it turns out that this is partial by, the correct change of coordinates is the polar coordinates. When you do that, this vector field becomes partial by partial theta. Okay? So you have to do something. Parvez, do you take back your objection now?
Partial by partial phi.
Well, depends on what.
Rotation around the z.
No, no. I donate the rotation around the z-axis as
Fine, you can go from one basis to the other. This is just transforming between bases.
no, but you have to do some work. You cannot just say that this is d by d. You have to find it out. You have to compute something, right?
Well, we like to understand it in simpler terms. More
No, but it's simpler term don't empower you. We want a calculus which will tell us how to compute these things out, right? If I give you any commuting arbitrary field, I mean, how can you say that this is partial by partial x1 and you have to do some work, okay? So, G, Dr.
Why did you write 1 here? X squared dx tilde by dx is equal to 1. This condition.
Because I want it to be d by dx tilde. I want a function. So this is not 0, of course, when x is not 0. So away from 0 I can divide and integrate, right? Okay. So to find canonical coordinates you have to solve some PDEs, right? And there is a systematic method to do it.
But you have just told us that when we go from one coordinate to another coordinate, we have to have this Jacobian. And I need to find out the determinants to get a number so that...
No, the Jacobian will only tell you that this is an invertible transformation. It will not tell you how to, those will not be canonical coordinates for a given vector field. I mean, look at what could be simpler than 1D. Here's a vector field in 1D. We know what are the variable is x. The x is a coordinate function. I still have to find, right? Okay. So, okay. So, how to find for a single field, and I will just do it in 2 dimensions, single field. We do it in two variables. Okay. So let x be a vector field in 2 variables. We want to find a function functions u and v. Of course, x be a vector field which is not 0 at some point p. We want to find function u and v defined near this point so that xu is equal to 1 and xv equal to 0. I want, so why is this enough? Because we know why. So we know that x in any system of coordinates is some function of those coordinates times partial by partial u plus another function of those coordinates times partial by partial v. So we know that x is equal to auv partial by partial u plus buv partial by partial v. So what is x of u? What is x of u? Plug in here. U and v are independent variables. Means partial u by partial u is 1 and partial u by partial v is 0. So what do you get for x of u? A of and x of v? B of uv, right? So if we can find the function u and v, so that xu is equal to 1 and xv is equal to 0, then what is x in this chord? Partial by partial u. So if so if x of u is equal to 1 and x of v is equal to 0, then x is equal to partial by partial u. Okay. Those functions for which x of v is 0, they are called the invariant functions, okay, for the vector field. Okay. So there is a method which goes back to Cauchy and it's called Cauchy's method of characteristics. Invariant of the vector field. Constants of motion? Well, I showed to you.
Cyclic coordinate.
Cyclic coordinate also. Why do you want to confuse us? Okay, so yes, there exactly. So for example, if I give x is equal to d by du, what will be an invariant for invariant function for this? A function f of u and v is invariant if partial f by partial u is 0. So f must be a function of only v, right? Okay. So step 1. So let let x be equal to axy. This is the given in the given coordinates xy plus bxy partial by partial y, and x at p is at a point p is not 0. So step 1 is find invariance of x using Cauchy's methods of characteristics. I will tell you. Of characteristics. Characteristic is nothing but an old the name for integral curves. Okay. So in the references which I am going to send you, you can read up the details in the book of Olver on partial differential equations. It's written for undergraduates. You can read it from there. But I'll also explain to you here right now. Okay. So and for existence of canonical coordinates, there is a book by Arnold on ordinary differential equations. You can look up why they exist. Okay, but once we assume that they exist, then this is what we have to do. Okay, so you use the let CTBN let C from some interval I into my open set. What did I give any name? Be an integral curve for So what is the meaning of integral curve? C prime t is the value of x at Ct. So C prime t is the value of x at Ct. So let Ct be the components of t be xt and yt. What is C prime t? C prime t is x prime t and y prime t. So C prime t is equal to x prime t and y prime t. And what is x of Ct? Is a of as as a vector valued function, what is x? X has components ax, y and bxy. So let's see. So otherwise we can't compare as a vector valued
If I
function.
look at x, I can also write this as a dot product of. It can be written as a dot del, right? And then it can also be related to the directional derivative.
Of course, that's every vector field can be so every vector valued function can be identified with the differential operator, which is the directional derivative in the direction of the vector field. That's what we did, right? So as a vector valued function, x at a point xy has components axy and so what is x of Ct? A of xt yt and b of xt yt. Now compare these. So x prime t x prime t is a of xt and yt, and y prime t is b of xt and yt. So this is, so along any integral curve we have dx by dt is equal to a of xy and dy by dt is equal to bxy along any integral curve. Okay. So do you see something very interesting? Dx over a is equal to dy over b is equal to dx over a is equal to dt, assuming that a is not 0, right? And dy over b is equal to dt. So along any integral curve, dx over a is equal to dy over b. So along any integral curve, dx over a is equal to dy over b. So okay, so when you solve, so solving this, I'll show this. Solving this gives you an invariant function, an invariant of an an invariant of x, okay, and call this invariant, give it any name, because the way I've set it up, let's call this invariant y tilde, okay, call this invariant okay, and what functions do we have to play with? We have this function, original coordinate functions x and y and y tilde. So from linear algebra, so by the way, functions whose Jacobian is not 0 are called functionally independent. So by linear algebra, there must be one of the coordinate function which is linearly independent from y tilde. Okay, so there must be one of the original coordinate functions must be one of the coordinate functions, say x, which is functionally independent of y tilde. Okay, so let's call this call this x tilde. Okay, so in the coordinates, how much time do I have left? Oh, good. So in the coordinates,
I have a question.
Ji.
What you are doing here in the method of characteristics,
Yes.
when we do PDEs,
Ji.
so basically once I write something down like this.
But I'm telling you know already.
No,
These people don't know.
I understand.
Yeah.
I'm just trying to understand that whatever you are doing in principle, we are converting a function of many variables into one variable. So to say, converting a PDE into an ODE to solve it and then
Converting a PDE into a simpler form.
okay, so
Into a simpler form.
a naive person like me would generally, call it an ODE because now
No, it's not an
PDE
ODE.
is
It's not an ODE. If I give you, so here's the result. If I give you any system of PDEs, homogeneous, right? Homogeneous and of order, I mean, first order, yeah.
Yes, first order.
Then you can introduce coordinates so that the system becomes partial by partial x1, partial by partial xk. No matter what, okay? And I will prove this in the class also if I have time, or maybe I'll refer it to some paper. It's a paper of myself called on computing joint invariants. So I've shown in that paper that when you give me any algebra of vector fields, finite dimensional, the joint invariants of that are the same as the algebra of vector fields obtained by reducing the coefficient into reduced row echelon form, and then it is abelian. It's quite surprising, right? A non-abelian system can be reduced to an abelian, generically, of course, away from singularities. Okay, but then we are getting into, so in the coordinates, x tilde, y tilde, we have x is some a x tilde y tilde partial by partial x tilde plus b x tilde y tilde partial by, right? Now I have not used, this is true for any system of coordinates. I have not used that y tilde. So what is x of y tilde? Is on the one hand it is 0 and on the other hand it is b of x tilde y tilde. So b of x tilde y tilde is 0, right? So now x of y tilde is equal to 0 because y tilde was an invariant. So in these coordinates x is equal to a times x tilde y tilde partial by partial x tilde, right? And now, so my problem is very much simplified. Remember that this is not 0 at my initial point, so it is not 0 in some neighborhood. So now I have to find a function, I have to find x double tilde, find function x so that x of okay. So we take so a x tilde y tilde partial x double tilde by partial is equal to 1, and x of so I can take okay, and how do I do this? I just integrate. So partial x tilde double tilde by partial x tilde is equal to 1 by a of okay. So how do I do this? Is the integral of this, therefore integral of 1 over okay, and y double tilde is equal to y. So in these I have completely straightened out my vector field, and this is a constructive method, you know. In books there are of course theoretical methods, but this is really very constructive as long as you can do the you can solve for characteristics. Okay, Dr. Waqas, is this in characteristics? Do you teach them in the okay?
In BVP, boundary value problem.
In boundary value problem, but there are many tricks, right? You can you can add them, and if dx over a is equal to dy over b, then d of x plus y over a plus b, and this kind of tricks. Huh? So okay. So let me do it for 3. Actually, I sent Claude this my handwritten manuscript, and it typed it and it omitted this. I don't know why. The difficult part. It made a decision on its own. So anyway, so let's do it for 3. So I even don't have to. So let's now do it for 3 variables. Do it for 2 vector fields. for two commuting vector fields. So let x, y be vector fields. It becomes only interesting if I go 2 also you can do, but let's do it for 3. Be vector fields in 3 variables, x, y and z. Okay. So x is equal to, now x, y, z which do not with xp and yp linearly independent. Independent at a, see, do you see now why I spent so much time in the first lecture on linear independence? And I mean, you cannot do you cannot do anything without understanding linear algebra and advanced calculus. These are the pillars. Okay. So linearly independent at P. So if they are linearly independent at P, can xp be 0? When you have a 0 vector field, this is always linearly dependent. So xp is not equal to 0. What did my result just tell you? I can find coordinates in which x is partial by partial x, right? So since xp is not 0, we can introduce coordinates in which x is partial by partial x, right? Now, y is equal to a times xyz partial by partial x plus bxyz partial by partial y plus cxyz partial by partial y, right? Y commutes with x, what does it mean? Y commutes with partial by partial x means, now partial by partial x bracket y is 0, right? Because I assumed these fields were DG, XYB commuting vector fields. Okay, so what does it mean? How do you compute the Lie bracket? You just differentiate. Okay, this formula becomes very simple. So therefore, so partial A by partial x, partial B by partial x is 0, and partial C by partial x is equal to 0. So in these, therefore x is equal to partial by partial x, and what is y? It will be just a function of y and z. Y is equal to let's go ayz partial by partial x plus byz partial y plus cyz okay. Now, look at this vector field. It's a vector field in how many variables? It's a vector field in 2 variables. Can it be 0? If it is 0, then y is a y z, those x and y would at that point become linearly dependent, right? So this vector field at the point P is not 0. So by induction I can assume I can reduce change of variables in y and z. So this is partial by partial y tilde. Okay. So you see the one variable case is really the key. So, and this is all you can program it actually. So now y is equal to a by z partial by partial x plus, let's give it some name, capital Z, where Z is a vector field, is just a field in 2 variables, byz plus cyz partial by partial Z. Okay? And Zp is not equal to 0. Otherwise, the original vector field would be linearly dependent at that point. So by change of coordinates in the yz variable, I can write it as d by. So by change of coordinates, in yz plane, by change of coordinates y tilde z tilde I can write z equal to partial by partial y tilde, right? And then
Hassan sir, I have a question. When
Ji.
you put, let's say, byz partial y plus cyz partial of partial z is 0. So even then, no, a here, see here, over there, you multiply by a by z.
G.
So if you say that this will become linearly dependent, how come? Because you are
Yeah.
multiplying with a variable, not by a constant.
But wait a minute, absolutely right. Suppose this is 0,
Yeah.
then y is a by z partial by partial x. Okay. So let's suppose that P has coordinates alpha, beta, gamma. Okay. So what is y at P? Is a times a at beta gamma partial by partial x at the point P, right? Is this not a multiple of partial by partial x? Right? I said those vector fields are linearly independent at one point. Okay? Actually, if they are linearly independent at one point, they will be linearly independent in a neighborhood of that point. Anyway, does it answer your? Yeah, it's an optical illusion. You think that, oh, here is this, how can it be? But this is a function, right? But when you evaluate it, it becomes a constant. Okay, and so, okay. So where was I? Okay. Okay. So in these coordinates, I did not do anything to x, right? And y is equal to y is equal to ayz partial by partial x plus z tilde was partial by partial y tilde. Okay. Oh, and then this will become okay. So we so for convenience, let's assume write y tilde is equal to y, z tilde is equal to z. So x is partial by partial x and y is equal to ayz partial by partial x plus partial by partial y. Okay. So, and finally then I have to find functions x tilde, y tilde, z tilde so that x is equal to partial by partial x tilde and y is equal to partial by partial y tilde. Okay. So partial by partial x is equal to partial by partial x tilde. What does it tell you about x tilde? Put x tilde here, right? Partial x tilde is equal to 1. So x tilde is equal to integrated x plus some function of y and z, right? And then y of x tilde should be equal to 0. If you plug in, so just to save, how much time do you have?
1 minute.
1 minute. So okay, just to save time, let me. So this is 0. If and only if ayz partial g by partial y is 0, right? And you can take y tilde is equal to y and z tilde is equal to z. So, no. Pyz, if and only if I forget something. If and only if ayz plus partial g by partial y is equal to 0. Now, can you not integrate this? Bring it to the other side and integrate this with respect to y. Okay? And what's the beauty of this? This works for any number of commuting vector fields, and the method is constructible. Okay? You have to use a method of characteristics to find invariants, and then you use simple integration to find the full canonical system of coordinates. Okay. So this was very abstract, but in we can do some exercises. Do you want it next time or in the break after the lunch?
Next time.
Next time, okay. You are fed up, huh? Okay. Yeah.
यहाँ पर ये cyclic coordinate x पे
क्या चीज?
वो जो invariant
एक्स इनवेरिएंट नहीं है, वाई और जेड इनवेरिएंट है. एक्स तो आपने पार्शियल बाय पार्शियल एक्स लिखा है ना, एंड यू हैव रिटन वाई एज partial by partial y, right? If you are thinking of a single vector field, any function of y and z, if we are in higher dimension, would be an invariant. But here we have this coupled system. And if we have n commuting vector fields whose values at a point are linearly independent, then you can write them as partial by partial x1, the other one as partial by partial x2, and so on. Unfortunately, Claude omitted this while typing from my, I don't know why. It makes some editorial decisions on its own.